Hello students, welcome back to chemistry online class brought to you by Hayoto Virtual Learning Platform. I am Olabisi Olawoye, your chemistry tutor, and this is the second part of the first topic, which is chemical bonding, which has been extracted from the WAEC syllabus and then backed up with past questions at the end of the class. And so the topic we are teaching today is formation of stable compounds from ions and then IUPAC nomenclature. And I want you to stay tuned in the class. So just pay attention because there are past questions at the end that will help you they will enable you to gain more knowledge on the topic treated on how to attempt WAEC questions. So I want you to pause the video at the end of this class, treat the questions, and then come back to watch the solution to the question. So the formation of stable compounds from ions. Actually, before compounds can be formed, elements combine, different atoms of elements combine together. It can be the same element or different elements, and they do so by transferring or complete transfer of electrons or sharing of electrons. That was what we did in the first class, which results into chemical bonding. And so they also achieve this literally to form they actually achieve this without showing the aspect of chemical bonding. They achieve this by exchanging their valence electron if they are different, and if they are the same, these ions are usually cancelled out. That is, whenever they give out the electrons or lose or the electrons or they accept electron, they become ions. So these numbers of electrons on top of such ion, for instance now calcium has atomic number of 20. Arranging it, we have 2 8 and 8, making 18. Then the last shell takes 2. So what happened here is that there are 2 electrons here, 8 electrons here, 8 also here. So the last part here is 2. So calcium has valence electron of +2, which is usually given out to chlorine, which will gain 1. Chlorine has atomic number of 17. So arranging, we have 2 8 7 2 2 2 1. So here now chlorine is in need of 1 electron. That is signified as minus, because whenever element gain electron which is negative, they become negatively charged. So there is a kind of exchange of valency here because they are different. So calcium here takes -1, but when it is written down, it becomes atom. So the sign here will no longer be useful. And then chlorine here, this 2 of calcium goes down to this side, and the positive sign here disappears. Is no longer needed, and so this represents number of atoms. And in most cases, we don't write 1. So the formula of the compound form is calcium chloride. That is CaCl2. The next one here is potassium. I'm going to mention the valence electron, but atomic number of potassium is 19. So arranging, we have 2 8. The first shell takes 2, the second shell takes 8, next shell 8, and the last shell takes 1. So we have positive potassium giving out 1 valence electron because it cannot gain 7, and then chlorine gaining 1. So because they are carrying the same number or different charges, they cancel out, and there's a kind of electrostatic attraction to give you potassium chloride. Also, there is also interaction or formation of compounds between magnesium and tetrose of a 6 ion. Tetrose of a 6 ion here represents a radical. A radical is a group of atoms of elements with charges on them. They form part of a compound. They don't exist alone. They can be positive or negative. And don't forget that positive ions are also radicals. They are called cations, while the negative ions are called the anions as well. But these ones, they are a group of atoms of elements. They are not compounds themselves, because they are not neutral. Compounds are neutral. So when we merge an element, magnesium, which carries +2 charges, because the atomic number of magnesium is 12, we have 2 8 and 2. These 2 valence electron will be given now because it cannot gain 6 more. And then the tetra, which is 4, oxygen, sulfate, which is sulfur, 6 ion, which is from the oxidation number, which we treated in the next part of this class after this part. So this gives us SO42-, and there are other charges that we need to know. Apart from the SO42-, we have SO32-, we have chloride ion, we have fluoride ion. These are just elements. We have NO3-, Cr2O7-. These are charges that we need to learn on our own. We need to know the charges they carry. You can find them in your textbooks. So these radicals carry a charge of -2. Now, because between the magnesium and the tetrahydrosis ion, they carry equal charge, they cancel out, though the numbers are not the same. So we end up getting MgSO4. So if they carry the same charge, they cancel out. If they are different, they exchange their valence. And this is a compound being formed, a stable compound being formed. So we have series of formulas resulting from the formation or from combining or exchanging of compounds, of valences of different elements together to form compounds. So this is a basis by which compounds are formed, and then that leads us to naming of ionic compounds. For simple ionic compounds, we use IUPAC nomenclature or IUPAC system, which is known as International Union of Pure and Applied Chemists. And this is a new way of naming compound, because most times you see in some the old way of naming compounds, when you see SO4 2-, you call it sulfate, and for WAEC students you're supposed to call it tetraoxosulfate 6 with the oxidation number assigned to it. So the knowledge of oxidation number is very important in the use of IUPAC method or IUPAC system for naming simple ionic compound. That is the most acceptable method for naming compound, especially in your exam. So we have rules for assigning oxidation number to different elements. Now these are the rules. The oxidation number of a monoatomic ion, that is a single element that has accepted ions, electron, for instance, become negatively charged. The charges it carries on it represent the number of electrons it has accepted, and because it has accepted, the electron is negative. It has given out, it becomes positive, and this is the number of electrons it has given out. So the oxidation number is the charges they carry on them, which is +3. The oxidation number of ion 3 here is +3, while bromide ion is -1. The next one, the oxidation number of hydrogen in a compound is always +1, because most times hydrogen has atomic number of 1, and it is assumed that it's part of the electropositive electron, though is a gas. If it has given out its electron, it is +1. Except in metal hydride, that is when it combined with sodium and sodium, it becomes metallic hydride. That's like sodium hydride, where the oxidation number is -1. So it can also combine with another metal, that is element that usually give out the electron, like magnesium hydride. The oxidation number will change to -1. The oxidation number of oxygen in a compound is always -2. Like the atomic number of oxygen is 8. So arranging it, we have 2 and 6. So it gains 2 more to make a stable octet structure at the outermost shell. So it's always -2 because it has gained 2 electrons. But in the case of peroxide, like if it's combining with another element that carries a charge that carries atoms of 2 as well, these are called peroxide. The oxidation number will change to -1. So we should take note of these laws when we are trying to calculate the oxidation number of different elements, and they are supposed to be used appropriately. So to get the correct name, the oxidation number of an uncombined element is 0. That is molecules of nitrogen, oxygen. When you see elements in this form, and when they have not combined with other radicals to form another compound, though they are molecules in this case, the oxidation number is usually 0. So for any neutral compound, for instance now, sodium chloride, that is between sodium and chlorine, they have cancelled out. There's a kind of attraction here, and they are now neutral because the positive and the negative charges have cancelled out. The oxidation number is also equals to 0 because sodium is carrying oxidation number of +1, while chlorine is -1. The last part here is number 6, which is for a polyatomic ion. The sum of the oxidation number must be equal to the ionic charge of the ion. That is, this is a radical, for instance. Example of radicals I was talking about, CO3 2-. The oxidation number of this radical is -2. So this is the -2 on top of it here. So when calculating the oxidation number of this radical, we end it with -2. Now we also have another rule here for binary compounds like potassium chloride. That's between potassium and chlorine. They usually end with "ide", except in water. You know, this is hydrogen and oxygen, it's also binary, but we call it water. And then ammonia, nitrogen and hydrogen, we don't use "ide" for them to end their names. But like hydrogen bromide now, potassium chloride, we use hydrogen chloride. They are binary number, and then we use "ide" to end their name. And then for element that carries more than one oxidation number, it is good to write their oxidation number in Roman figure at the center of their name, like iron 2, iron 3 oxide, copper 1 oxide, copper 3 oxide, and so on and so forth. that leads us to the past question aspect. I want you to pause the video here, treat these questions, and then let's come back to solve the questions together. I want you to attempt this question on your own now, then after which you come back and we solve it together. Welcome back to the past question series. So the first question here is WAEC 2013 number 3. The formula of the compound formed between a trivalent metal heme. Trivalent means it has 3 oxidation number, or it has 3 oxidation number on top of it, and a divalent non-metal. Y is what? So if M is trivalent, that's +3, and if it is a metal, metals are usually positively charged, then divalent plus -2, which is a non-metal. What is the compound form? But you do this by exchanging the valence. So we have M2Y3, and take note that any letter that is given to you, especially if the question is asked in theory, that's what you should stick with, except otherwise stated that you should indicate or get the name of the possible compound form. But if you are not asked, please just use the letter as it was given. Determine the oxidation number of sulfur in H2SO4. That's another question here. Now, normally when you want to name a compound, I'm going to use this question to establish or to illustrate the way of naming compound using IUPAC nomenclature. What we do is that we get the oxidation number of the central element first. Locate the central element. When you get the oxidation number of that central element, then use it to name the compound. How? We start with the first element, then we go back to the last element, then the central element will be named last with the oxidation number written in Roman figure. So for the last element here, at times we may have oxygen. If you have 2 oxygen, we di. If you have 3 oxygen, we have tri. If you have 4 oxygen, we have tetra. And in some cases, we have poly. For here now, let's quickly calculate the oxidation number of hydrogen. Here, hydrogen carries +1, always +1, and there are 2 atoms of hydrogen, so we have multiplied by 2, plus sulfur, which is just single 1. Assuming you have 2 sulfur here, multiply by 2. Then oxygen, the oxidation number of oxygen is -2. Why? Atomic number of oxygen is 8. 2 on the first shell, 6 on the second shell. It gains 2, so -2 because it's gaining. Multiplied by the 4 here, everything is equal to 0 because the oxidation number of this compound is 0, is neutral. So working this out, we have 2 plus sulfur plus -8 equals to 0. So we have S on this side, 8 on the other side, going to the other side. With this +2 here going to the other side, we have S as 6. So if the oxidation number of sulfur is 6 here, the name of this compound is... So the next question here, okay, before we can do that, before we are going to treat that, let's quickly name this compound after getting the oxidation number. The name is actually hydrogen tetraoxo sulfate. This is hydrogen tetraoxo sulfate 6. That's Roman figure 6. And it's a compound, so we don't end the name with aeon. The next one is, there are the IUPAC name for each of the following compounds, WAEC 2015 theory, NaClO3. Before we can write the IUPAC name, target the central element, calculate the oxidation number. Sodium is 11. It gives out 1 because it's 281. It gives out the only 1 electrons. It's just 1 atom here. We have +1 in bracket, plus this chlorine that we want to calculate, plus oxygen, which is 8. Atomic number is there, so we have 2 and 6. 2 on the first shell, second shell is 6. It gains 2 to become -2 because there's a need of 2 more to make it 8. And we have 3 atoms of it, so everything is equal to 0. +1 plus chlorine plus -6 equals to 0. Plus times minus is minus. Carrying it to the other side, we have chlorine as 6 minus 1. So chlorine is 5. To name this compound, we name it as sodium trioxochlorate 5. Now, the last one here is copper. The next one here is copper. We have to locate the central element, which is sulfur, before we can name the compound using IUPAC nomenclature. So copper has +2 because for this compound, this is a heavy element. So most times we can deduce their oxidation number from the from the radicals they combine with. Now for this compound to have been formed, it must have contained +2, and the tetrasulfate 6 has -2, and they cancelled out. So it means that copper is +2 here, +2 of copper, plus the sulfur here, plus -2 of oxygen times 4. Now leave this one aside. This 5H2O. We don't need to calculate the oxidation number. Then after working this out, we have 2 plus sulfur plus -8 equals to 0. That's 2 plus sulfur minus 8 equals to 0. Sulfur equals to +8. Coming to this side, -2. Sulfur is 6. So from here now we have the name as copper 2 tetra for oxygen, oxo sulfate with oxidation number 6. Now with this name, penta, 5 is penta, water is hydrate. So that is the full name of the compound. Then here we have this. We were asked to calculate the oxidation number of sulfur. This is a sulfur. So in this case now we have sodium, which is 11. It has oxidation number of +1 multiplied by 2, plus sulfur, which is carrying 2 atoms, plus oxygen, which is -2 because the atomic number is 8, 2 and 6, it gains 2, multiplied by 2 because we have 2 atoms of it, everything is equal to 0. So 1 multiplied by 2 here is +2, plus 2s, plus -4. Don't forget that when element gives out, they become positively charged. Sodium is 11 here, is 2, 8 and 1. It has given out 1, that's why it's positive. And the oxygen here is -2 because it has gained 2 electrons. So we have 2 sulfur here, plus times minus is -4. Carrying it to this side becomes +4, plus 2 here carried to the other side, that is -2. Sulfur equals to 2. 2 sulfur equals to 2, dividing both sides by 2, we have sulfur as 1. So the oxidation number of sulfur here is 1. The last part here is number 5, which is WAEC 2013. Number 4. An atom of an element X gains 2 electrons. The symbol of the ion formed is, because it has gained 2 electrons, it's going to be electronegatively charged, because any element gaining electron becomes negatively charged, because the element they are gaining, the electrons they are gaining is negative. So there will be a decrease in oxidation number, unlike elements losing to become positively charged, there is an increase in oxidation number. So the best answer here is X2 minus, because there is a gain of 2 electrons, so it's negative. That brings us to the end of the class. I must commend your effort for paying attention to the end of the class, and I want you to subscribe to this channel by watching more videos on IOTA virtual learning platform. Thank you. God bless you.